In 9.2, we're going to talk about specific ways in which we can traverse the edges of a graph and visit the vertices. We're first going to define a path of length k. If we have an undirected graph and a positive integer k, then a path of length k between vertices v1 and vk plus 1 is a sequence of k distinct edges such that e1 connects the first two vertices in our path, so the v1 through vk plus 1. We're going to designate v1 as whatever the starting vertex is, and then vk plus 1 is the ending vertex. So we have edges connecting v1 and v2, and then v2 to v3, v3 to v4, and so on, until we get to our last edge, our kth edge, connecting vk to vk plus 1. Now, in this book, the way that a path is defined, the edges may not repeat, but a vertex can show up multiple times. And if the graph is simple, then we're not going to have any loops, and so a vertex is not going to be repeated consecutively. So it may show up multiple times in the path, but it's not going to appear right after itself. Now, as the book mentions in the footnote at the beginning of 9.2, the terminology surrounding the ways in which we're going to be traveling around a graph is not universal. So the way that we're defining path here may not be the same as you would see in another book. So as you're reading through a book dealing with graph theory, you want to be aware of that particular author's use of terminology. And depending on the context, it may not be immediately clear, but they may be using these terms in such a way that it indicates that, say, you can or can't repeat a particular edge or vertex or something like that. So be mindful of the way in which it's defined in your particular context. So let's look at an example here. We have this graph, and a path from A to D, for instance, could look something like this. Let's go ahead and highlight that instead. So traveling from A to B to C to E to D gives us a path, in this case, of length 4 from A to D. And the way that we can denote a path is to simply write out the vertices that appear. So we could say A, B, C, E, and D, and assume that we're going to be connecting those. So as long as those are connected by edges, then we know that we have a path. We could also look at, say, this sort of path, A to E to B to C to E to D. So that would also be a path connecting A and D. It would have length 5. I do have a repeated vertex. We went A to E, B, C, E, and then ended up at D. I've repeated E in that, but that's allowed in our definition. We're not allowed to repeat any edges, and I didn't do that here, but I did repeat a vertex, and that's okay with the book's definition of a path. A circuit or a closed path of length k is a path of length k where the starting and ending vertices are the same. So for instance here, if I were to just continue on from D to A in either of these, then that would give us a circuit or a closed path. Now, a simple path or a simple circuit is one in which no vertex is repeated, except in the case of a circuit where the initial and the terminal, the starting and the ending, need to be the same. A simple circuit is also called a cycle or a k-cycle. So in our examples above, the first one is simple, but the second one is not because of that repeated vertex. Looking at another example here, are these sequences listed here paths? If so, are they simple? Are they circuits? What's the length of each one of those? So let's go through and just trace out each one, and we'll see if we can traverse along this graph between the vertices. So going from A to E, and then to B, to C, and then back to B. Now that would be length 4, but I've repeated an edge, so that would not satisfy our definition of path, and it also wouldn't be simple because we repeated an edge. And it's not a circuit because we didn't end where we started, and not simple, again, because of repeating. We could see that we repeated B as a vertex. So even if we hadn't repeated an edge, then this still would not have been a simple path. And then looking at the second one, so there we're told to go from A to E to A. Well, that's already a problem. D, B, C, and then we have another problem. We can't go from C to A. So there are two issues. We have a repeated edge, and we're told to move between two vertices that are not neighbors. They're not connected to each other. Looking at the third one, let's trace that out. Going from E to B to A, well, that's a problem right away. We don't have an edge between B and A. From there, A, we could go to D, and then from D we could go to B, and from B back to E. That would have been another problem, though, because we would be repeating the edge between B and E. So there are two problems with that one. Looking at the fourth part, going from C to B to D to A to E to C. That is a circuit or cycle. In this case, we have 5 edges that we've traversed, so that would be a 5 cycle. So that one is allowed. Looking at some other examples, here we should be able to find cycles. We could just go around the outside edge. There may be others as well that we could follow. So there's another one that we could follow all the way around. But in the second one, the only one is going to be to go around the outside edge. These graphs are not isomorphic to each other, and we could go through and show that. Something like 14, we could travel through all of these vertices without repeating. So we can have that simple path or simple circuit if we don't want to complete it. And this is just another view here. We do something like that to complete a simple circuit. Now an Euler path is, and that's the correct pronunciation, it's not Euler, it's Euler. An Euler path is a path that uses every edge of G exactly once. And then Euler circuit is a circuit that uses every edge of G exactly once. So because it's a path, we are allowed to repeat vertices. We're not allowed to repeat edges. And the distinction here is that we're using every edge exactly once. A graph is said to be Eulerian if it contains an Euler circuit that contains every vertex of G. So we could have an Euler path or an Euler circuit in an unconnected graph, although that's not quite as interesting. We could have vertices that aren't connected to any of them. So an Eulerian graph will need to be connected. Path that goes through every vertex exactly once is called a Hamilton path. So in our examples up here, these are Hamilton paths. A cycle, a simple circuit that passes through every vertex exactly once, is called a Hamilton cycle or a Hamilton circuit. And those definitions can apply to both directed and undirected graphs. With a directed graph, then we have to be following them in the correct order, so that gives some additional restrictions there. And it may be possible to find the Euler or Hamilton path or circuit if we have an undirected graph, but if we add direction to those vertices and no additional ones, then it may not be possible anymore. So if we look back at, we'll have some other examples as well. For instance, here, this is not an Euler circuit because we did not use every edge once. There were some edges that were missing. It is a Hamilton circuit, though, because we have used every vertex exactly once. This 5 cycle was a Hamilton circuit, but not Eulerian because it didn't use this edge right here. So let's go down and look at a few more theorems and some other examples related to Hamilton and Eulerian paths and circuits. Euler's theorem says that if we have a connected graph with at least 2 vertices, multigraph is an undirected graph in which multiple edges are allowed but no loops, and simple graphs are a subset of the multigraphs. And so this theorem applies to our simple graphs, which is generally the context in which we're going to be working. But as long as it's connected, then this theorem holds. G has an Euler circuit if and only if each of its vertices has even degree. It's going to have an Euler path, but not an Euler circuit, if and only if it has exactly 2 vertices of odd degree. And the vertices of odd degree are going to need to be the starting and ending vertices in that path. And then the third part to that theorem, G does not contain an Euler path or an Euler circuit if it has more than two vertices with odd degree, because these were both if and only if. So let's look at some examples. Next three theorems apply to Hamilton paths and cycles. Let's come down here, find an Euler circuit if we can, and if it doesn't, try to do an Euler path. We can first go through and check and look at all of the degrees. Since those theorems are if and only if, that'll tell us if we have a situation in which we can find those. So we've got degree 2 here, degree 4, degree 2, degree 4, 2, 4, 4, 4, and 2. So we have all even degrees here, and looking back at Euler's theorem, that tells us it's going to have an Euler circuit. So it should be possible to find a circuit here that goes through and visits every edge exactly once. So one possible solution, and I'll just draw it out here, is to traverse in this way. So starting at this degree 2,
come down here, up, down, over here, go here, and then up, over here, come back here, travel around like that.
So I am repeating vertices, several of them multiple times each, but I didn't repeat any edges, and I used every edge exactly once. So we have an Euler circuit, but looking back at our theorem, we didn't have two vertices of odd degree, so there's going to be no Euler path in this particular graph. So there's no way to visit every edge exactly once without coming back to where you started, or without creating a circuit there. Then looking at this example, let's go through and write out our degrees. We've got degree 3, degree 4, degree 3. So there's 2 degree 3s. Hopefully that's all. Otherwise we know automatically that we won't have an Euler path. We already know that there's no Euler circuit. Degree 4 and degree 4. So there is going to be an Euler path, but no Euler circuit. And the theorem said that we're going to need to start and end at the vertices of odd degree. So we'll use that, and again try to go through and visit every edge exactly once, doing something like this. So that's one possible option. Again, I hit vertices multiple times, but I didn't repeat any of the edges, and I used all of them in that particular path. So let's go back up and look at the theorems related to Hamilton cycles and paths. If we have a simple graph with more than 3 vertices, such that the degree of v1 plus the degree of v2 is greater than or equal to the number of vertices for every pair of non-adjacent vertices v1 and v2 and g, then we know that g is going to have a Hamilton cycle. If we have a simple graph with more than 3 vertices, such that the degree of each vertex is greater than n divided by 2, greater than or equal to n divided by 2, then g has a Hamilton cycle. And if we have a simple graph with n greater than or equal to 3 vertices, and at least 1/2 times n squared minus 3n plus 6 edges, then g is going to have a Hamilton cycle. And in all of these theorems, in the corollary, theorem 5 is called Orr's theorem, the corollary here is also called Dirac's theorem. In all of these, the idea is that there are going to be enough connections, enough edges, when we're looking at these degrees here. All of the vertices have enough edges that there's no way to not have a Hamilton cycle. Now, in order to satisfy these, we're going to have quite a few edges. And so there are going to be many instances when we have a Hamilton cycle when these theorems are not satisfied, when they're inconclusive. So if the hypotheses are not satisfied, then these are all going to be inconclusive. If we don't have the number of edges, basically, that need to appear in order to satisfy these conditions, then we can't say, based on these theorems, whether or not we're going to have a Hamilton cycle. In that case, we could go through, if we can find one just by inspection, by trial and error, then we could perhaps show that it has one just by an existence proof. Let's go down and look at these and see what is satisfied. So if we go through and let's first count the number of edges. So we have 14 edges in this first one. And we already have our degrees written down over here. The number of vertices in this case is equal to 9. So looking back at our theorems, Orr's theorem says that all non-adjacent vertices have to have degrees summing to greater than 9. Well, looking at these, even if they're not adjacent, we have at most degree 4, and so that is going to be inconclusive. We're never going to get a sum greater than or equal to 9. So in this case, Orr's theorem is inconclusive. We have a degree sum less than or equal to 8 for all non-adjacent v1 and v2. So that doesn't work out. If we look at Dirac's theorem, that would say that all of them have to have degree greater than or equal to n over 2, which in this case means greater than or equal to 5, because we can't have a degree 4.5. So both of those are inconclusive. So if we look at how many edges we would need with the number of vertices that we have here, we're going to need 1/2 times 9 squared minus 3 times 9 plus 6, which is equal to 30 edges. Well, I don't have 30 edges here. I only have 14. So that corollary is also inconclusive. So none of those guarantee the existence of a Hamilton cycle. So since all of those are inconclusive, then we would have to go through and just by trial and error see if we can find a Hamilton cycle or a path. So we're trying to visit every vertex exactly once. Well, Hamilton path, that's going to be pretty easy. Just something like that will work. Hamilton cycle, if we try those, then we're going to run into issues. As we keep trying things, there's always going to be a connection that we need that isn't there if I'm going to be able to make it back around to where I started. So this one does not appear to have any Hamilton cycle. If we had an edge, so these diagonal ones, if one of them was turned the other way, or if we had another diagonal edge perhaps above these, then we could complete some of those paths that we were trying to traverse there. So coming around like this, if I were able to go over here and then connect, that would work out, but we aren't able to do that. So let's look at this example. We have our degrees already written out. We have a total of 6 vertices, and the number of edges in this case is equal to 11. So let's go up and look at our theorems again. Orr's theorem, so looking for a Hamilton cycle. Hamilton path is going to be relatively easy to find in these just by inspection. So I can go around and I can visit every one exactly once. And also while we're doing that, there's a Hamilton cycle for us as well. So let's see what the theorems say. So we know that we can find one, but let's go through and see what checks out with the theorems. Maybe the values here are such that it's going to work. First, if the sum of the degrees for all non-adjacent is greater than or equal to the number of vertices. Well, we have 6 vertices here, and looking at all of our degrees, we have the smallest degrees in here are 3, and those are both non-adjacent. So the degree of v1 plus the degree of v2 is always going to be greater than or equal to 6, even if they're not adjacent to each other. So that does work out. We have basically enough edges on enough of the vertices that it will work. So greater than or equal to 6 on all of those for, again, non-adjacent v1 and v2, but actually degree 1 plus degree 2 is greater than or equal to 6 anyway. So that guarantees that we have one. Looking up at Dirac's theorem, are the degrees all greater than or equal to n over 2? Well, yes. We've got 6 vertices and all have degree 3 or greater. Degree greater than or equal to 3, so we would get one there. Let's see if the corollary guarantees it this time. So we're going to have 1/2 times 6 squared minus 3 times 6 plus 6. which in this case is equal to 12. So this corollary is not satisfied. We don't have enough edges to guarantee the existence of a Hamilton cycle by this corollary. But the other two are satisfied, and so that guarantees that there is going to be one. Doesn't tell us how to find it, but we already found one without too much trouble. There's another possible example. So now we're going to look at weighted graphs briefly. We'll come back to these later on in chapter 13. A minimum Hamilton cycle in a weighted graph, which simply means that the edges now have values assigned to them, the weights. A minimum Hamilton cycle in a weighted graph is a Hamilton cycle for which the sum of the weights of the edges is as small as possible for any Hamilton cycle in that graph. And it may or may not be unique. There may be multiple Hamilton cycles that all attain that smallest weight. So here, looking at this example, if we're trying to create a Hamilton cycle and use the smallest weights possible on those, then one possible Hamilton cycle, we'll try to figure out if it's the smallest one. Well, that doesn't work out. I missed that vertex, so I'll have to go back and travel again. So the weight of that cycle is 10. Make a note of that. Let's try another one. Let's see if we can maybe use more of the weight 2. Well, that didn't do any better. We still have a weight 3 edge being used there, and we've got 2 weight 2s, just like we had in the previous one. So that gives us another weight 10. So just by inspection, it looks like that's probably going to be the smallest one. We need to try a few more options, but we've been using almost all of the weight 1 vertices. There's one left out in each of the 2 that we already attempted. We could try some other options, but it looks like that's going to be about as good as we can do. So if we were to do something like, we'll give it one more shot here, but if I'm trying to use, say, all of the weight 1 edges, then I'm going to end up in a situation where I'm not able to get back without repeating something. So I'm going to go up there. If I try to start over here using all the weight 1 edges, I can't ever use that one. So we're going to be running into problems as we're trying to move around the graph and use all of the weight 1s. We're going to end up using at least a weight 2 and a weight 3 on that. So it looks like the minimum weight for this particular graph is 10. We'll have algorithms in the weighted graphs and what are called minimum spanning trees, not quite a Hamilton cycle, but minimum spanning trees later on in chapter 13.